Well, hello there. Let's do shear stress video 2. In this video, we will calculate shear stress. As a reminder from our previous videos, if you have a beam that's loaded in any which way, and you want to find the shear stress in that beam, there are two things you have to choose. One is, where along the beam do you want to calculate the shear stress? And two is, where along the cross section, let's say that this is a T-beam, where in the T-beam do you want to calculate the shear stress? So if you were calculating the shear stress at this location, and then you said, well, I want to find the shear stress at the centroid or a half inch from the top. So we need both of those pieces of information. Where along the beam tells us what the shear force is. So if we know where along the beam, we can go to the shear and moment diagram, or we can calculate the shear. Once we know where along the beam, we have the cross section. Now we can calculate I. It's the same everywhere for the cross section. And then Q and T depend on where in the cross section we are. All right, let's calculate shear stress. So the other day, in one of our previous videos, we had a beam that was loaded like this. So it had 3 kilonewtons per meter distributed load, 4 meters long, 2 meters and 2 meters. We went and calculated the reaction forces. We then drew the shear diagram and the moment diagram. Well, let's pick a point on this beam to calculate the shear stress. Let's just pick this point 1 meter in, and 1 meter in. The shear load, the V, is 1.5 kilonewtons. And we'll use this cross section here, the 40 centimeters, the 10 centimeters, and the 10 centimeters. So shear stress equals 1.5 kilonewtons. That's the V. And then in that same video, we took the time to find the centroid. The centroid was 0.26 meters from the bottom. And then we used the parallel axis theorem to find the I for this cross section about its own centroid. And we got 0.000945 meters to the fourth. So let's divide this by 0.000945 meters to the fourth. Now we need Q and T. And we need to decide, where are we going to calculate the shear stress as we go up and down the cross section. Let's see. Here's a diagram where we talked about Q in a previous video for a T-shape. And for our T-shape that we're dealing with here, we've got the dimensions of 0.4 and 0.1, 0.1, and 0.3. meters. And as I said, we found the centroid to be 0.26 meters from the bottom. Well, let's find the shear stress. Let's find it twice. Let's find it at point, let's call this point X, and have it be 0.1 meters from the bottom. And then let's find it at point Y, and point Y can be at the centroid of the flange, 0.05 meters. So we're going to find a QX and a QY. QX, we'll do X first, is now we take the area from point X to the outer fiber. Area is base times height, and we have 0.1 meters is the base. 0.1 meters is the height. And now we need the distance from the centroid of the whole cross-section down to the centroid of this piece. Well, if this is 0.1, its centroid would be 0.05 and 0.05. I think I can say, well, 0.26 is from the centroid to the bottom, come up 0.05, and we would have 0.21 meters. And better do a little math here. Equals 0.1 times 0.1 times 0.21. Probably could have done that in my head. 0.0021 meters cubed. Pull that out of the way. 0.0021 meters cubed. Then we're also going to need T at point X, and T is the base dimension, and that is 0.1. So let's see, this is I, VQ over IT. Q was 0.0021 meters cubed, and T, that's Q, and T is 0.1 meters. Well, what happens to our units? Let's see, we've got meters cubed up top and meters to the fifth down below. That's going to leave us down below with a meter squared. We're going to have kilonewton per square meter. That's what we would expect for a stress, is a force per unit area. Another name for a kilonewton per square meter would be a kilopascal. So tau x, just at point X, is equal to 1.5 times 0.0021 divided by 0.00945 divided by 0.1, and I get 3.33 kilonewtons per meter squared, or 3.33 kilopascals. .5 times 0.0021 divided by, oh, I missed a zero. Just double checking my math here. I missed one of these three zeros. And that makes this 33.33. All right. So what I'd like you to do now is I'd like you to do tau y. And I will put this back up. So it's VQ over IT. I want you to decide what to use for V, what to use for I, what to use for Q, and what to use for T. Once you press pause and do that, well, before you press pause, I'll put this back up so you can find Q at point Y and T at point Y. Okay, pause. All right, well, you should be back. And you need to find QY. I got a little space up here. And TY. QY would be the area from point Y to the outer fiber times the distance to the centroid. Well, the area, the height here is 0.05. The base is 0.4. So we have 0.4 times 0.05 times, now we need a distance. If this is 0.26, then this is going to be 0.14. 0.14 minus 0.05 is 0.09. So there's your Q. Equals 0.4 times 0.05 times 0.09, 0.0018 meters cubed, and Ty is, what's this base dimension? 0.4 meters. So you should have chosen the same 1.5 kilonewtons, the same 0.000945 meters to the fourth. For Q, we now use 0.0018 meters cubed, and for T, 0.4 meters. Put that into my calculator. And I get 7.14 kilonewtons per meter squared. See, that's a smaller number, that's a bigger number. Bigger in the denominator, smaller in the numerator, going to be smaller. Okay, so there's tau y. And there's a good example. Have a good day.